So this video lesson is the second of two parts that go over the concept of scientific notation. And just so that we can remember, review, and be clear, scientific notation is what we use to represent large numbers. We can actually use it to represent very, very small numbers too, but the way we're looking at it, it only represents large numbers. And all numbers in scientific notation have the same form in two key parts. First, we have this number c, and that number c is some number between 1 and 10. It could be 1, but it can't be 10. And that c is multiplied by the x power 10 to the n, where n is just some whole number. It could be positive, it could be negative, but for right now, we are only talking about n's that would be positive and therefore be talking about very, very large numbers. So in terms of what we did in the last video lesson, where we looked at numbers that were written in scientific notation, like the two here, 3.96 times 10 to the third and 1.537 times 10 squared, both of these numbers from the last video lesson, we would now want to talk about what we would do in reverse. That is, taking a standard form number and changing it into scientific notation. But we're going to re-look at the process of changing something from scientific notation to standard form as a way of illuminating that process. So if we remember how to work with numbers in scientific notation, if you don't, go ahead back and look at that video lesson. We have 3.96 multiplied by 10 to the third. So we're going to take our 3.96, and I'll rewrite it here, 3.96. We are going to rewrite it, or rather we already have rewritten it, and now we're going to move the decimal point by the number of places indicated by the exponent. 1, 2, 3. Going to have to add another 0 because we've moved one more place than digits that we have, and our decimal point now goes here at the end. Therefore, our new number is 3,960, which is the number represented by 3.96 times 10 to the third. Now, if we look at our other number, 1.537, 1 and 537 thousandths times 10 to the second. Again, let's rewrite our number here so we have it a little bit bigger. Multiply it by 10 to the second power. The second power indicates we should move the decimal point 2 places. And so therefore we now have 153.7. And so this is the process for changing something from scientific notation into standard form. And what we want to do is we want to figure out what we can do to change the number now back from standard form, either 3,960 or 153.7 or any other number we have in standard decimal form, back to scientific notation. And in order to do this, we're sort of going to think of the process in reverse. First, instead of knowing what our digits are that we start with, we need to figure out what digits are going to be in our number. We have two parts of a scientific notation number. We have a number between 1 and 10, represented by c, and that is then multiplied by 10 to some power n. So in order to write it in scientific notation, we need to figure out what is c and what is n. Now, c is some number, and if you haven't recognized it from the previous video lesson and from the example here, this number c, which in the case of the first example is 3 and 96 hundredths, needs to contain all the digits of our number. Every one that we need is going to have to be contained within the c because the power of 10 to the second, 10 to the third, 10 to the seventh, eventually, but not right now, 10 to the negative fourth, there is going to be no digits added. It just moves the decimal place. So first, when we're looking at these two numbers, we need to make sure we know what digits we need. Now for 3,960, we need the digits 3, 9, and 6. And for 153 and 7 tenths, we need 1, 5, 3, and 7. So those are the digits that we need. Therefore, these are going to be the digits contained within our C. And so what we want is we want this number to be between 1 and 10. Be between 1 and 10. Now 396 is definitely not between 1 and 10, but if we put the decimal place between 3 and the 9, then it becomes 3.96, and that is between 1 and 10. it becomes 1.537, and that becomes between 1 and 10. So then that is going to be the C, that is the digit we need, that is what we want to have, and we just have to figure out how many places we need to move the decimal point to make 3.96 into 3,960. Well, if we work backwards, 3,960, you need to move the decimal place 1, 2, 3 places. So that means in reverse, to take it from 3.96 to 3,960, you would also need to move the decimal point 1, 2, 3 places. So this is going to be 3.96 times 10 to the third. And now for 153.7, we would need to move it 2 places to the left to make it 1.537. So to undo it, we just need to move it 2 places to the right. So then this then becomes times 10 to the second, because we only have to move the decimal point 2 places. And so this basically is the process for how we go through scientific notation. First, we need to figure out what our C is going to be. And we start that by thinking, what digits are we going to use? What ones do we need? Well, in this case, 2,475, we need all 4 digits. So once we decide we need all 4 digits, now we think, how can we make this number between 1 and 10? And 2,475 is not between 1 and 10, but 2.475, using the same digits in the same order, is between 1 and 10. So now we need to figure out how to make 2,475 into 2 and 475 thousandths. And in order to do that, we think, how many decimal places do we need to move? Well, from the original standard form number, we need to move 1, 2, 3 places. So in order to move it back, we would need to go 1, 2, 3 places. And so that means that our exponent is the number of places we need to move the decimal point, or 2.475 times 10 to the third power. Let's look at 2 more examples of that to go through that, and then we'll set you off with some problems to do on your own. So we're going to look at 2 other examples that have the similar digits, so that we can look at it and just look at some different ways of scientific notation and standard form might come up together. So in the example on the left, 247.5, we want the digits 2, 4, 7, and 5 in that order. Now, we want our decimal point to be between the 2 and the 4, to make this 2 and 475 thousandths, because that number is between 1 and 10. Whereas we put the decimal point anywhere else, between the 4 and 7, 24 is not between 1 and 10, 247 certainly is not between 1 and 10. And so now that we've got our C, 2.475, how many places do we need to move our decimal point? Well, to move the decimal point to where we want it to go, it has to travel 2 places. So therefore, our exponent needs to be a 2. 2.475, 2 and 475 thousandths times 10 to the second power. Now, if we look at 24,750, we might look at it immediately and think we need the digits 2, 4, 7, 5, and 0. But what we know about the digit 0, and actually, let's wait on that for a second. Let's find our decimal point first. Our decimal point, again, needs to be between the 2 and the 4, because 2.4750 is between 1 and 10, whereas 24, 247, 2,475, etc. are all not between 1 and 10. So this turns out to be the C that we are looking for, 2.475. Now we need to figure out how many places we need to move our decimal point. Well, to get the decimal point back to 2.475, we need to move it from the original number 1, 2, 3, 4 places. And remember, I included the comma here for a specific reason, and that's that the comma does not represent a distinct place value. It's merely an indicator that we're changing from the ones, tens, and hundreds to then the 1, 10, 100, thousands. Ones, tens, hundreds, millions, billions, trillions, etc., and moving the designation for those place values. It is not a place value unto itself, so it really is just 1, 2, 3, 4 places. So this needs to be represented times 10 to the fourth. And if you're thinking to yourself, well, we don't need this 0 at the end of the number because a 0 at the end of a decimal is not significant, we can just drop those, especially if there's no digits to the right of it, and you are absolutely correct. If you were to leave it there, it wouldn't be incorrect, certainly, and it would be representative of the fact that there is a 0 at the end of 24,750, but in the decimal place values, in the 10,000ths place value, which it is in our C, it's not significant and we don't need to keep it. So go ahead and pause the video and see what you can do with these 4 problems. 13,400, 99 and 45 hundredths, 120 and 5 thousandths. Take a look at those zeros and see if you can identify how they might be different than the zeros in, say, 13,400. And finally, 26.2. Well, let's start with 13,400. We want the digits 1, 3, 4, definitely. And we can add the 0, 0 at the end just for good measure. And so we want this to eventually become 1.34 because that number is between 1 and 10. So in order to get that decimal point to that place, we need to move it 1, 2, 3, 4 places. So this needs to be multiplied times 10 to the 4th. Now again, we don't necessarily need to keep the zeros. We can get rid of them. Or we can keep them if you want to. However, they are not necessary. For number 2, 99 and 45 hundredths, we want the digits 9, 9, 4, 5 in that order with that orientation. And that means we want our decimal point between the two 9s, so it is now 9 and 945 thousandths because that number is between 1 and 10. To do that, we only need to move the decimal place 1 space, so we only need to multiply this by 10 to the 1st. 1 is our exponent, 9.945 times 10 to the 1st. Now, I said before you started working to consider how the zeros in 120 and 5 thousandths might be different from the zeros you saw in 13,400. And in this case, we want not only the 0, we want not only the 1, 2, and the 5, but we want all the digits 1, 2, 0, 0, 0, 5. Because even in decimal places, the zeros become significant if there is another digit off to their right. And if we dropped the zeros and had just 1, 2, 5, I'll show you that in a second, the wrong way to look at it so that we can see what the difference is. First, take a look at the way that we want to do it. We need to move the decimal point 2 places, so this just needs to be times 10 to the 2nd. 1.20005. Now, if we wanted to look at what would happen if we left the zeros out, 1.25 instead of 1.20005, it would still be times 10 to the 2nd, but that would give us 125 instead of 120.005. So this is actually something we don't want to do. That is the incorrect way of going about it and dropping those zeros that are in the middle of a number. And then finally, for 26.2, we want the digits 2, 6, and 2. We need to put the decimal point between the 2 and the 6 so that it becomes a number between 1 and 10, and we only need to move it 1 space, so this just gets multiplied times 10 to the 1st. So as a quick review, when we are looking at standard form numbers to go to scientific notation, the first thing we're going to do is figure out what our C needs to be, what digits we're going to use, which ones do we want to keep. Then we're going to figure out how we can make it into a number between 1 and 10, where do we need to put our decimal point, and then finally, how many places did we move that decimal point. And the last thing I'll leave you with is just that number that we started the first video lesson on scientific notation about, Google. Now remember that Google is 1 followed by 100 zeros. So the question I have for you to work on as a challenge if you want to, but you don't necessarily need to, and to bring it into class tomorrow when you come, is that if we have the number Google, which remember is just 1 followed by 100 zeros, how would you write this number in scientific notation?